get through the first part of this. So yesterday was find lengths of the sides in a right triangle, and today is going to be about, part of it anyway, will be about the measures of the angles. So grab your packet and find that example that we were at. We went through quite a bit of this.
Yeah,
We got the bigger things.
We did. We did.
Oh, yeah. Give me any blank.
Did the airplane?
Yeah,
We did the airplane.
We already did. That's too far. That's
Well,
too far.
looks like we're almost done then, huh?
You gotta step back. Just a step back to keep it.
Oh, there is a hole in your notes.
Yeah.
Right down here. There it is. So, given any two sides in a right triangle, well, you're just asking for one of these from the homework. You know, you have two sides. You can use the inverse trigonometric functions to find the measures of the acute angles. That's what they're for. You know? What we get when we punch in cosine, sine, and tangent is the ratio of two sides in a triangle. But what we're putting in is the angle measure. So inverses, remember, the input and the output switch. So what we do is we give them the ratio of the two sides of the triangle, and it pops out the angle measure for us. So that's what those inverses are for. Because sometimes it drives people nuts that, and I know it did when we did this too, that -1 notation, you know. But that means inverse in this case. It's not raising it to the -1 power. It's just the way that we symbolize that inverse of tangent. So that's what we're going to use today. Again, your calculators need to be in degree mode. You know, everything we do with this book is going to be in degree mode. And in number 5, it says, in triangle DGH, angle H is a right angle. And like I've said before, I'm a picture person, and it absolutely helps you set up your trig as far as SOHCAHTOA goes. So here we have an H. I'll just put the D over here. DGH. Doesn't make any difference if I did D up here and G down here. You just have to have that 90-degree angle in the right spot. And then they tell us little h is 13. And at first you say, well, how am I supposed to know where little h is? Well, in geometry you learned wherever you have the large letter for the vertex, opposite that is where the lowercase letter goes. So if this is a big H here, this is a little h over here. They're always opposite. That's how it's set up. So this will be a little d over here, and this will be a little g over here. So opposite that capital letter is where we get the lowercases. And then it said h is 13 and g is 5. And what they want us to find, and we could actually find both of the acute angles that are missing, but they want us to focus on D. So I'm going to circle D here. Because what I have to do is think of, from the perspective of D, if I'm standing at that vertex D, what would be the labels for the 5 and the 13? Because that determines which trig function I need to use. So out of opposite, adjacent, and hypotenuse, which label should we give the 5? It is the adjacent. How about the 13? Hypotenuse. So again, SOHCAHTOA. If you were wondering yesterday, how are people getting that so fast? You think in your brain, okay, I need adjacent, hypotenuse. Which primary trig function is going to do that for me? Yeah, cosine is adjacent and hypotenuse. So the cosine of angle D equals 5 over 13. But we want to undo it. So we're going to punch in the inverse of that 5/13, that ratio of those two sides, equals the measure of angle D. And they didn't say to the nearest whatever, so maybe we'll just give them tenths, since the homework. Inverse cosine 5/13. There it is. So about 67.4 degrees. Measure of angle D, approximately 67.4 degrees. Again, that little bubble for the degrees is huge. If that's not there, then it's assumed that we are doing this in radians. And since we haven't discovered radians yet, that'd be awful hard for us to do. So there it is, 67.4 degrees. So easily we can find G. We know this is 90. We now know this is 67.4. Every triangle has 180 degrees. Wouldn't be a big deal. So down here it says, oh look at that, they even gave us pictures. Didn't even have to draw our own pictures. What is the measure of angle A in each triangle and use the trigonometric ratio? So I'm going to have you go after that and get you a candy partner and see if everybody's remembering their geometry.
Grass, yes.
Well, let's just go ahead and stop this one. Candy up in there, find your partner. That way if anybody is stuck, it didn't look like anybody was, but that way you can check in and say, which street function did you use?
Yeah.
This one, they still wanted us to find the measure of angle A. So you look at A, and you say this is opposite, and this is hypotenuse. So katoa, that's sine. So the sine of angle A is 4/10, and then we take the inverse sine, and if you wanted to reduce it, you could. It doesn't make any difference. But something we should notice as we're going through this, sine and cosine will always be a number between -1 and 1. Always going to happen when we're talking about our triangles. In fact, for everything we do with the triangles, it should be between 0 and 1 because it should be positive. But while I'm writing this down, I want you to explain to your partner why it's going to be between 0 and 1. Sine and cosine.
Anything more than 0? Yes.
Who heard something good? For y, we're always going to have sine and cosine between 0 and 1.
Go, Samo, you got it.
Sam, did you say something good he heard?
Not really.
No?
I don't know. I
He's
figured,
just putting you on the spot.
I figured he'd have a good answer.
I heard some good explanations. I was eavesdropping. Why will sine or cosine, both of those, always be between 0 and 1? Oh, so you have it. Exactly. Both of them are divided by the hypotenuse, and the hypotenuse will always be the longest side. So no matter what, we're going to have a smaller number over a bigger number. It's going to happen. The only time it wouldn't happen is when we're not talking about right triangles, because if we had an equilateral triangle, then things would be a little bit different. But We're talking about the triangles we're working with, which is right triangles, so it'll be between 0 and 1 every time. And sometimes that's a way to know that you've punched something in that makes absolutely no sense. If you accidentally forget to do degrees on your calculator, you use radians, sometimes you'll get a negative answer, and you're like, a negative angle? What is this? And then you'll realize, oh, I don't have this in degrees. So those type of things are generally helpful. And it is a way for you to use multiple choice tactics when you take the MCAs or the ACTs, because if your choices say which one of these absolutely cannot be the sine or the cosine of an angle, and they give you these choices. Tell your partner which one of those absolutely did not be the sine or cosine of an angle. Let's see. So it's a way to say, this is the one right here. It's bigger than 1. Can't happen. When we're talking about a right triangle trig, it is not going to happen. So down here, it says we're going to use the inverse of a trigonometric function for actually something that people will do this in real life. It says construction. You must build a wheelchair ramp so the slope is not more than 1 inch of rise for every 1 foot of ground. Well, already I see an issue. They got 2 different labels here. We can't do that. We need to have the same labels. So I know they like their little 1 foot down here, but I'm going to change that to 12 inches. And what they just said was the rise over run, which is the slope, cannot be more than that. Well, 1 over 12. So that's our max. Now notice that doesn't have labels in it because it was 1 inch over 12 inches, so the labels just totally drop out. That means it doesn't matter what the labels are in the future. That's the fraction we need to see. So it says, what's the maximum angle that the ramp can make with the ground to the nearest 10th of a degree? Well, this is opposite, and this is adjacent. So tell your partner which trig function we're going to need to use. Then let's do it. Inverse tangent of our little 12. Well, let's go 4.76 since it's so tiny. We'll use an extra decimal there, so about 4.76 degrees. Oh, wait a minute. They did tell us what to round to. They wanted tenths. Fine. Be that way. 4.8 degrees, which is not much. 4.8 degrees is not much of a slope. But it's a wheelchair ramp. It's not supposed to be something where they get halfway up and they lose their strength and now they're in the street. It's not supposed to happen that way. So that's the whole reason that they'll have, and it's called code, they'll have code that tells them this is the highest slope that you can make a wheelchair ramp. So now, we're building a ramp. An entrance to a building is not wheelchair accessible. Right now, they can't do it. And so because it's a business and code now says they have to be wheelchair accessible. The entrance is 6 feet above the ground. So there's our 6 feet above the ground. And 30 feet from the roadway. So there's a road over here. It looks a lot like a river right now. So that's 30 feet away. A says, how long must the ramp be for the slope to meet the regulation of 1 inch of rise for every 1 foot of run? We know 1/12 is supposed to work here. And they're asking us, hey, this ramp, what would we need to do? Well, this is 6 feet right here. We want to know how long would that ramp have to make this work? And again, our 1/12 doesn't have any labels on it. So it's perfectly okay to use that along with the 6 feet over something. It's just our answer is going to be in order to get this. So we'll have x equals 72 feet. Problem. Take a look at the drawing. Do they have 72 feet? No. So do we move the road? No. So in B, it says, how could you build a ramp that would make this happen? Justin's exactly right. Some of you probably weren't here when we had the portables out back. Maybe you still were. Raise your hand if you were here when we had the portables up. Yeah, remember we had a ramp that had to kind of wind around. Yeah, that's what you have to do. So you can't go directly across the road. You wouldn't want to make, like we have those bypasses, bridges that go over a road. That would be really hard for a wheelchair person, all of that stuff. So what you do is you'd make something that has kind of a stopping point where they could stop and it's flat and then go down again, and then you'd have to do another one and go off to the side. And since I'm a really bad drawer, I went ahead and put that here, an example of something like that, where it's coming off to a side, going down, and then there's maybe a flat spot for them to make sure that they still have their strength before they go back down another one. It's doable. You just have to think of different ways to do it. So, 43210, inverse street functions. Everybody know? Looking good. Thank your partner for their wonderful help. I have never been to Europe, but I had a girlfriend, well, I have a girlfriend who's been over there a couple of times. And she said one of the most noticeable things that happened when they went to Europe was her mother would need a wheelchair every once in a while to get around where she needed to go. Nothing in Europe is wheelchair accessible. And there are people in wheelchairs at grocery stores who have to just sit outside the store and wait until somebody notices them and comes out and asks them what they want before they go in and get their stuff. So, we're definitely doing it the right way here and I understand their buildings are incredibly old. So, making all of those changes would be very, very expensive. But for somebody that's handicapped, it really is tough to get around in Europe.